All right. And then all my lectures will be posted online. If you go to my YouTube page, you'll notice that there's already a calculus lecture series from last year. So I'll just make this calculus. I think at the end of it, I'll put something like 2020 or something like that, so that it's clear what lecture that is. Or maybe I'll just change the name of the playlist, Calculus 2020, and then just put the videos up as normal. So the videos will have the same name, but it will just be a different playlist. So all the videos will be up online. I should typically be able to get those up the same day that we have the class, so this lecture should be back up online. You understand how grading works. Is there any other bookkeeping stuff that we need to do before we just jump in, or are we ready to just go?
Is it possible to find a physical copy of our textbook?
A physical copy? It should be. So the copy of our textbook is very common. This isn't one of those classes where I'm using some old obscure textbook. This is a textbook I found. I was specifically trying to find a calculus textbook that does a hybrid. I wanted it to go through how a normal calculus text does, going through the application problems, but I also wanted to rigorously develop the theory. So I wanted something that did both those things. In searching that, specifically this textbook that we're using came up a lot. I don't love the textbook. I was going to switch it to an easier one, but since it was U3, decided I didn't need to worry about that. So we'll continue with this one for this year, and then next year I might switch it up if I'm still teaching. But it starts out very fast paced. So the author goes through the preliminaries very, very quick because he's kind of assuming if you've gotten to this textbook, you're pretty familiar with mathematics, which he was expecting college students, not high school students. So we're going to take plenty of time going through all the preliminaries, make sure that we cover everything that we need to cover. If there's anything fuzzy that we cover, you need to stop me and we need to make sure it makes sense. I can't stress this enough. This is not a class where something goes away. If you do not understand a concept, it's not going to disappear. We're going to be building up, building up, building up. Everything builds on itself. So there's only 3 of us here. There's no reason that we can't thoroughly answer each and every one of your questions. Right? We have plenty of time. There's no restriction. There's no requirement, hey, we've got to cover this much material this semester, or this year. There's no requirement that says that. Far, far better that we cover half of what I want to cover and everyone understands it, then we get one person all the way through to the end. So let's make sure that we understand the material, make sure that there's nothing fuzzy, and we'll build up from the foundation. Now, natural question, why do I teach calculus like this instead of teaching regular calculus the way everyone else teaches calculus? Why do I build it up so hard? The main reason is because I don't view this class as teaching you calculus. The point of this class, the same reason I teach something like discrete math, is my goal is to get you to learn how to think deductively, to logic and reason. That's the goal. The goal is to help you learn how to reason, help you learn how to logic. We're just using calculus as a medium. We're just developing some interesting field of mathematics because it's interesting, but that's not the purpose to develop the field. The point is to get you comfortable doing this, taking some set of premises and looking at their logical implications, learning how to logic, learning how to reason. That's my goal here. And this is just material that we happen to be using. They had a class called calculus that they wanted me to teach, so I'm teaching calculus material, but the point is to teach you the reasoning aspect of it. The thing I tell students all the time is 100% of the time, anyone who can do the theory can do the application problems. I've never come across someone who could prove what derivatives were, but struggled solving a derivative. It's never been the case. I could count almost every student that I went to school with who knew how to solve a derivative, but didn't know a proof to save their soul. And even really simple proofs. Couldn't do it. So I focus on the theory because when you come across this stuff later, when you go to college, you'll be fine with that. You guys will be able to get to that just fine when you come across it. It's a theory that you're going to trip on. It's a theory that you're going to stumble with. So I think it's even more valuable to rigorously develop this because unless you go to college to get a math major, you'd never come across this material again. They would just start on a high level and just teach you how to solve calculus problems as opposed to teaching you calculus. So we're going to develop it from the ground up as we go. And if we're going to develop it from the ground up, we got to go all the way back back to reasoning. Now, this is a conversation I think I've had with everyone in this class already, but never hurts to have it again. So going all the way back to reasoning, there's 3 different types of reasoning that we're allowed to do. What's reasoning? It's how we justify some conclusion. It's the reason we give for our conclusion. That's what reasoning is. And there's 3 different ways that we can justify our conclusion. One of them is deductively, which is what we use in math and logic. It's the only type of reasoning we're concerned with in this class. Deductive reasoning, we all know the common example. If all men are mortal, and if Socrates is a man, then Socrates is mortal. Is a common example. Now notice that you don't have to know who Socrates is, you don't have to know what man is, and you don't have to know what mortal is for that sentence to still be true. If all men are mortal, and if Socrates is a man, then Socrates is mortal. I could say, if A is a member of B, and B is a subset of C, then A is a member of C. Captures that exact same type of logic. If I say all A's are B's, and if I say A is a member of B and all B's are C's, then A is a C. Another way of saying it. So notice that we never said that Socrates is a man, and we never said that all men are mortal. We said if Socrates is a man and all men are mortal, then Socrates is immortal. It's the implication that we're saying is always true. It's universally valid. If we were to try and imagine in our heads a completely new universe with completely different laws of physics, so, some 5-dimensional universe with 2 dimensions of time, who knows what that would even be like? Whatever beings evolve in there, say some intelligent beings evolve in there, we can't teach them our physics. It doesn't matter in their universe. We can't teach them any other field of knowledge that we have. It doesn't matter in their universe. But all our logic and math still applies. It's universally valid. It's in no way contingent upon this universe. Make sense? Deductive reasoning, that's the type of reasoning we use. It's knowledge to the extent that we can claim knowledge. If we can say anything is true, we can say a mathematical proof is true. It's a tautology. It's a statement that's always true. Inductive reasoning. What's inductive reasoning? We remember?
It's a lot of observations.
It's
generalization on a lot of observations.
It's generalizing observations. Generalizing phenomena. Typically observations when we're talking about science. So, inductive reasoning is the reasoning that you think the sun's going to come out tomorrow. Inductive reasoning is the reasoning you think that if I let this go, it's going to fall. Why do you think that? Because every time you've done something similar, that's what's happened. Is it physically possible I let this go and it doesn't fall? Is that a possibility? There's no remote crazy scenario that could possibly occur that makes I let this go and it doesn't fall.
Yeah, it's possible, I suppose.
Yeah, it is possible. We could have some big object flying above the Earth the instant I let go of this, and it's close enough that its gravitational pull on this object is exactly equal to the gravitational pull of the Earth, and the second I let go, it just hovers there for a second. And as the object passes, it falls. That's possible. Highly, highly, highly improbable, and so science would take it into consideration, but still a possibility. Right?
Okay, but that's not proving your point on inductive reasoning.
Well, my point with inductive reasoning is that it's not foolproof. It's dealing with, this is what's most likely going to happen.
Yeah.
But it's no guarantee. Just because you've seen something happen 100 times, 1,000 times, 1,000,000 times, even if you've seen something happen infinitely many times, it's still not a guarantee that whatever rule you're observing holds. And the simple example is thinking about, I can prove inductively that every number is even. Check it out. 2, 4, 6, 8. You tell me how many examples you want, I can give you that many examples of numbers that are even. Therefore, every number is even. It doesn't work. So that's the shortcoming with inductive reasoning. We have to use it. It's what you have to do in the field of science. You have to inductively reason. You observe something over and over again, and we say, okay, we're going to call it a law of physics, a law of nature, that this is always the case. But it's no guarantee. It's far from a guarantee. And so we don't have to use that type of reasoning in math because that's very dangerous reasoning and we can easily come to very crazy conclusions like every number is even. Doesn't work. And then the third type of reasoning is abductive reasoning. So inductive reasoning, we look at phenomena and we create generalizations. I take this object, I drop it, I drop it, I drop it. I carefully measure it every time it falls, and I say, it's accelerating downwards at roughly 10 meters per second squared. I come up with some law of nature. When you drop objects, they accelerate downwards at 10 meters per second squared. I create some generalization, right? And then I can use that generalization as I'm developing my science, but I use that generalization. When we're doing abductive reasoning, we're doing the opposite of the opposite. And some sort of counterpart to inductive reasoning. So inductive reasoning, we look at a bunch of phenomena. We look at a bunch of phenomena and we create some generalization of that phenomena. Abductive reasoning, we take our generalizations to reconstruct a specific phenomena. So when I say the law of gravity, I'm talking about how objects have always fallen in tons of different scenarios. When I use abductive reasoning, I'm going to recreate a particular scenario using my generalizations. And the example I like to give is the kid who takes the chocolate chip cookie. You leave a little kid in a room with a chocolate chip cookie, you walk out the room, you wait a minute or so, you come back in the room, you see that the cookie's gone and the little toddler has chocolate and crumbs smeared on their face. Your conclusion would naturally be that the child ate the chocolate chip cookie. But that's not a safe conclusion. For all you know, there was someone else hiding in the room. The second you left the room, they came out of their hiding spot, ate the cookie, saved the chocolate chip, smeared it on the kid's face, went back to their hiding spot. You come back in the room, you get mad at the little kid for eating the cookie. It was a safe conclusion. It's the type of conclusion that you have to use, or it's the type of reasoning that you have to use in that scenario. But it's far from foolproof, and it's the type of reasoning we have to use when we're reconstructing historical scenarios. It's the type of reasoning we have to use in a court of law. When we say you prove something in a court of law, we say you've proved it beyond a reasonable doubt, and that's the best that we can do. It's weaker than a scientific proof, which is weaker than a mathematical proof. So this is all that we're concerned with in this class. And it's the only type of reasoning that we're allowed to use in math and logic. So that's the foundations. We're going to use deductive reasoning. Okay. So moving from this we're starting logic, unless we have any questions. Okay, logic. So in all of math, we're talking about statements, and we're interested in whether or not statements are true or false. And it's just an offshoot from logic. You use logic to develop your math. So we're going to start with a statement. What's a statement? A statement is a sentence that is either true or false, but not both. Pretty straightforward? Good? Okay. Statements. We have some ways of combining statements. One of the ways that we have of combining statements is called the conjunction of the statement. So if A and B are statements, then the statement A and B we call their conjunction. Now notice I said, well, we'll go to disjunction real quick and then we'll make that point. We also have the disjunction of two statements. If A and B are statements, then the statement A or B is their disjunction. Now notice I said the statement A and B and the statement A or B. So if A and B and the statement A or B are statements, then what do we know? We know that they're either true or false. Right? So if I know that A is a statement and I know that B is a statement, then I'm saying A and B is a statement. So how do I determine whether or not A and B is true or false? Similarly, how do I determine whether A or B is true or false? And so we have our truth tables for doing this, and hopefully you all remember the truth tables. If the statement A is true and the statement B is true, that little symbol right there is an and. So if the statement A is true and the statement B is true, then the statement A and B is true, right? And if A is true and B is false, then the statement A and B is false. If A is false and B is true, the statement A and B is false. And if both A and B are false, then it's true. Then it's false. Good. Right? Remember? Okay. Similarly with or. Now remember with or, in terms of logic, we're talking about the exclusive or the inclusive or, not exclusive or. So let's remember the difference on those really quick. So in the English language, when I say or, I might say Donnie's in room 5 or he's in room 2. Now, you understand that when I say that sentence, I'm either in room 5 and not in room 2, or I'm in room 2 and I'm not in room 5. But I'm not in both. That's the exclusive or. That's not the case that we mean here. We mean the inclusive or. We mean both cases are valid. We mean it like when we say, Donnie's holding an eraser or a piece of chalk. Is it true that I'm holding an eraser or a piece of chalk? Yes. So we mean the inclusive where both being true is also true. So let's go through it real quick. So if A is false and B is true, A or B is?
True.
True. If A is false, B is false, A or B is?
False.
False. Wrote these in a weird order. Make sure that you guys aren't just memorizing some order. If A is true and B is true, A or B is?
True.
And if A is true and B is false, A or B is?
True.
True. Wonderful. Okay, so that's conjunction, that's disjunction, negation. Negation, the one that seems the most straightforward. If a statement, if A is a statement, then the statement A is false is its negation. We also say not A. So remember, we're saying that A is false is a statement. And we need to determine the truth value of this statement from A. So if A is true, the statement A is false is?
False.
False. And if A is false, then the statement A is false is?
True.
True. Sorry, that seems a little weird. Room 2. And then we also say not A, that's the not symbol. We're good with that? Okay. Now, a point we always need to hammer home a little bit is when we're talking about the statement not A, we're talking about A's contradiction. Now, when two statements contradict each other, that means one of them has to be true and one of them has to be false. Notice if A is true, not A has to be false. And if A is false, not A has to be true. Okay? So let's see this in action. We're going to come up with contradicting statements. All swans are white, so the contradiction of that statement is some swans are black, right?
No.
No, because what if we live in a universe where all swans are blue? If we live in a universe where all swans are blue, which of these is a true statement and which of these is a false statement?
They're both false.
They're both false. So these are just
But we don't live in a universe where all swans are blue.
Remember, logic and math is no way dependent on the laws of this universe. These have to be statements that are universally valid, no way contingent upon what you know about the universe. And for all you know, okay, well, let's not say that.
Some swans are black. Why is that not true?
Some swans are black.
How is that not true? What if we live in a universe where some swans are black?
We could. We could live in a universe where this is true and this is false. But just because you know this, so pretend that we have some portal into parallel universes. And I look into that universe, and I tell you in that universe that some swans are black. Well, that's not a good way. Okay,
so the opposite of A would be not all swans are white.
Perfect. The contradiction of all swans are white is not all swans are white, or some swans are not white, would be the contradiction of the statement.
Right. Okay, yeah, that makes sense. Yeah.
That makes sense?
Yeah.
Okay. Similarly, what's the contradiction of some swans are black?
No swans are black.
No swans are black. Some swans are black, no swans are black.
All swans are
One
black.
of those statements has to be true, one of those statements has to be false. Some swans are black, no swans are black. One of those statements is true, one of those statements is false, guaranteed every time. All swans are white, some swans are not white. One of those statements has to be true, one of those statements has to be false. Contradiction. So contradicting statements, one is always true, one is always false, guaranteed. Contrary statements just means they can't both be true. They might both be false, but they can't both be true. So these are just contrary statements. They can't both be true. They could both be false. Maybe we live in a universe with all blue swans. But they can't both be true. We can't have all swans are white and some swans are black. Make sense? Difference between contrary and contradicting?
Mm-hmm.
When we talk about the negation of A, we mean its contradiction. We mean that if A is true, not A is guaranteed to be false, whatever that statement is. And that's probably the weirdest part in logic, so if we're done with that, we're making good progress. That make good sense? Okay. So let's do it real quick. Let's do some negating. Let's come up with a contradiction. And let's look at how we do a contradiction for a conjunction. So what's the negation of Donnie is a teacher and Donnie is in room 5?
Donnie's not a teacher or Donnie's not in room 5.
Right. In order for this statement to be false, we either need this part to be false, or we need the second part to be false. Right?
Oh, because
So-
if they're both false, then it's true.
If they're both false, then it's true, but if they're both false, then it's true. If they're both false, then the statement's false. Or if at least one of them is false, then the statement's false.
So why can't we just make them both false?
You can, but we need the contradiction. I need to come up with a statement that if you know that this statement's false, you know that this statement's true. And if you know that this statement's false, then you know that this statement's true. So that statement is Donnie is not a teacher, or Donnie is not in room 5. So one of the two cases is for sure true, and one of the two cases is for sure false. Either Donnie is a teacher and Donnie is in room 5, or Donnie is not the teacher and Donnie's not in room 5. If this statement's true, this statement's false. If this statement's true, this statement's false. You see it? Let's fill out the truth table and get a feel for it. So let's look at the case where I'm the teacher and I am in room 5. So if I'm the teacher and I'm in room 5, then the statement Donnie is the teacher and Donnie is in room 5 is true, right? So the statement that I'm not the teacher and I'm not in room 5, the statement that I'm not the teacher and in room 5 is false. This is just a negation of this, right? This is the weirdest part in logic, so if you get this, you'll be good. So now let's look at this statement. That's this one right here. This statement right here is not A or not B. Donnie is not a teacher or Donnie is not in room 5. Okay? So let's analyze this one for the case where I'm the teacher and I'm in room 5. Donnie is not a teacher is false. Because we're looking at this case where I am the teacher and I am in room 5. So Donnie is not the teacher is false. Donnie is not in room 5 is false. False or false is false. False. Losing you in that?
I mean, it makes sense, but like, I don't see why it needs to go that.
So here's what we're going to do. We're going to go over the 4 cases where we're going to go over the 4 possible cases with me being the teacher and me being in room 5. And we're going to look at both these statements in that case. That's what we're going to do. So Donnie is a teacher and Donnie is in room 5 was true. That's this statement. So this statement is right here. That's this column. And this statement is this column. And the point at the end of the exercise is that this column and this column are really the same. The not of this statement is this statement. Right? So that's the point of the exercise.
That's
But
my
let's
whole question.
yeah, so that's what we need to make sense. Which is why filling out this is going to help you see it.
You just said that they're the same thing.
This is
My
going to turn
question
out to
is,
be the
why
same
do
as
we
this.
have to do, like, why can't we just do not A and B instead of doing not A or not B?
Because that doesn't
Okay,
work for all
so
cases.
let's look at not A and not B. That's a good idea.
No, not A and B.
Oh, not A and B?
Yeah.
Because the point of the exercise is to show you that the negation of this is this. Because that's a useful substitution to do a lot. Basically what we're saying is, look, when you distribute a not over an and, it converts it to an or. We're saying that this and this are the same.
Right, but why do we need to say that?
Because this is often a useful way to write this. And this is often a useful way to write this.
Okay.
It's just like, I mean, if you think about this as an operation, we're doing a distribution of a negative over something,
Right, I
kind
can
of.
see that.
And so it's the same reason that distributing in math is useful. There comes algebra problems all the time where you want to distribute across parentheses. So same type of thing. There often comes a situations in logic where you want to distribute the not. So we're just trying to get intuition for why this works on a high level. And then once it clicks in your brain, oh, duh, that's obvious, then it will make sense. So first case, Donnie is a teacher and Donnie is in room 5. The statement Donnie is a teacher and Donnie's in room 5 is true. The statement Donnie's not a teacher or Donnie's not in room 5 is false. Because that was false and that was false, so false or false is false. Let's look at the next case. Let's say I am the teacher, but now let's pretend we're in room 2. Okay? So the statement I'm the teacher and I'm in room 2 is false, or the statement I'm the teacher and I'm in room 5 is false. Is the statement I'm not the teacher or I'm not in room 5 true or false?
True.
True, because now we're in room 2, right? So let's look at another scenario. Let's say we are in this room, we're in room 5, but now let's pretend that Levi's the teacher, not me. So the statement Donnie's the teacher and Donnie's in room 5 is false. But the statement Donnie's not the teacher or Donnie's not in room 5 is
Donnie is the teacher.
we're doing the scenario where Levi's the teacher, but we're in room 5.
Right, so the opposite of that would be you are the teacher. Now I'm confused. If
Okay.
you're not the teacher and then we're doing opposite of A, how does that not make sense?
So we're in a universe now where Levi's the teacher. A is still Donnie's the teacher. The universe that we're in is Levi's the teacher. A is still the same statement every time. Donnie's a teacher. So let's just look at this sentence instead of looking at the logic for a second, and that might help. So let's pretend that we're in room 5, but Levi's a teacher. Now let's say whether or not this statement is true or false. Donnie is not a teacher, or Donnie is in room 5. Is that statement true?
Sure.
Sure?
Yeah.
Yeah, it is true.
That is so confusing. I don't understand that. If A is false, and then
Maybe
not A is true.
this is too wordy and it's making a mess. Let's just forget these statements for a second. Let's erase that. We'll fill in scenario by scenario with just chalk and marker, and I think it'll make more sense. Alright, so setting up the first scenario. A is holding a marker, B is holding the chalk. Is it true that I'm holding a marker and I'm holding a chalk?
Yeah.
Yeah. Is it true that I'm not holding a marker or I'm not holding a chalk?
No.
No. Next scenario. Is it true that I'm holding a marker and I'm holding a chalk?
No.
No. Is it true that I'm not holding a marker or I'm not holding a chalk?
No. Not true.
I'm not holding a marker or I'm not holding a chalk.
Oh, it's true.
It is true. Right?
Okay.
In this scenario, either I'm not holding a marker or I'm not holding a
Right.
chalk.
Okay.
Okay, next scenario. I'm holding a marker and I'm holding a chalk.
False.
False. No, that's fine. Once it clicks, it'll click. Next scenario. Get rid of that. I'm not holding a marker or I'm not holding a chalk.
True.
True. Finally, I'm not holding a marker, and I'm not holding a chalk. Sorry, said that wrong. This one. I'm holding a marker, and I'm holding a chalk.
False.
False. I'm not holding a marker, or I'm not holding a chalk.
Also true.
Also true. Which, there you go. It's a contradiction. When this case was true, this case was false. When this case was false, this case was true. Which would be exactly the values that we put here. False, true, true, true. Okay. So let's do another example. This time we're going to distribute the negative over a disjunction. So we're looking at the statement, I am tall or I am small.
Okay.
What's the negation of that?
I am not tall and I am not small.
Perfect. I am not tall and I am not small. So notice that when you negated an or, it turned into not and not. Similarly, when you negated an and, it turned to not or not. So when you distribute a not, it turns ands to ors, and it turns ors to ands. So if we were to do this, setting up the different universes, starting with the first case, I'm holding a marker, I'm holding a chalk. Is the statement I'm holding a marker or chalk true?
Yeah.
Yeah. Is the statement I'm not holding a marker and I'm not holding a chalk true?
No.
No, this one's false. Next scenario, I'm holding a marker or I'm holding a chalk.
Yeah.
True. Oh, we already have that. I'm not holding a marker and I'm not holding a chalk.
False.
False. Next scenario, I'm holding a marker, I'm holding a chalk. True, which I have. I'm not holding a marker and I'm not holding a chalk.
False.
False. Finally, I'm holding a marker or I'm holding a chalk.
False.
False. And I'm not holding a marker and I'm not holding a chalk.
True.
True. And once again, they're the contradiction of each other. So, not A or B is not A and not B. Similarly, not A and B is not A or not B. Okay, so that's it for negations. Let's move on to implications. So if A or B are statements, then the statement A implies B, or if A then B, are implications. And implications are also statements. So, do you remember how to do implies?
Yes.
If, let's set up the scenarios and just fill it out. So, I'm holding a marker, I'm holding a chalk. The statement, if I'm holding a marker, then I'm holding a chalk is, if I'm holding a marker, then I'm holding a chalk. Okay, so,
False.
no, it's true, but now you're going back to thinking in terms of our universe, and you're thinking, well, it's possible for the scenario where Donnie's just holding a marker to be true, and
Okay, but the
I'm not holding a
statement.
chalk. But the statement, independent of the universe, if all you know in all of existence is me right now holding this, there's no such thing as time, there's no such thing as laws of physics, this is the whole universe. Me, this state that I'm in right now, holding the marker and a chalk. Is the statement, if I'm holding a marker, then I'm holding a chalk, true?
No, I don't see how that. If you're holding a marker, then you're holding a chalk. That does not imply that.
You're looking for some sort of causation between those two things.
Okay, maybe if you give me a statement that we're going off of.
Well,
Donnie holds a marker when he holds a chalk. And then maybe it'll imply it. I don't understand it.
well, I need something that I can set up across a bunch of different scenarios. So we're in a universe where I am always holding a marker and a chalk. This is how it always is, always will be. Forever me just here. There's no such thing as time or anything else. I'm always holding a marker and a chalk.
Okay.
For all of existence now. And I always was, always will be. That's the universe. Donnie holding a marker and a chalk. There's nothing else. There's no world. There's no universe. Just me holding a marker and a chalk. Is it true that every time I'm holding a marker, I'm holding a chalk?
Yes.
Yes. If I'm holding a marker, then I'm holding a chalk.
Okay.
Right? True. New universe. If I'm holding a marker...
You can't just create all these different universes.
Yeah, we're setting up a universe where this is the case, a universe where this is the case, a universe where this is the case, a universe where this is the case. All we're doing is setting up universes where A happens to be true and B happens to be true. A happens to be true, B happens to be false. We're just setting up universes where these four combinations. Because the statements I'm using don't actually matter. I'm just picking statements that are easy to set up. So is it true that if I'm holding a marker, then I'm holding a chalk?
No.
No, that one's false. Next scenario. If I'm holding a marker, then I'm holding a chalk. This is a weird one.
No. True.
True. Now this is what we call vacuously true. When the implication, when the antecedent of the implication, the first part of the implication is false, it's always true. So let me give you an example. If I start any if-then statement with, if Donnie's a green dragon, then, whatever the then is, doesn't matter. That statement is always true. There's no cases to check. Donnie's never a green dragon.
Oh, alright, okay.
So it's vacuously true. There's no cases to check, so you can't call it false. That's another way that you can think about it.
Yeah.
If I'm holding a marker, then I'm holding a chalk. Is it false?
No.
No. So it's not false.
That's right.
So it's true. And then last case, if I'm holding a marker, then I'm holding a chalk.
True.
True. And then, another useful way of writing an implication that you might remember from discrete math is it's
Oh, yeah.
Contrapositive.
contrapositive. So, A implies B is ultimately the same thing as not B implies not A. And let's write out the truth table real quick. False implies false is
True.
true. False implies true is
True.
true. True implies false is
False.
true implies true is.
True.
And notice, what did I mess up?
You did not A implies not B instead of not B implies not A.
Oh, I did it backwards. I was supposed to do this implies this. Oops. Restart. False implies false is
True.
true. True implies false is
False.
false. False implies true is,
True.
and true implies true is.
True.
That's good, because that means you weren't just looking over here, because we got it wrong, because I said it wrong. Okay, now we say they're the same. So A implies B is the same thing as not B implies not A. So that's a useful substitution that we can do in our algebra of logic. We can make that substitution anytime we need, if it helps us think about a problem. Okay, so that's equivalences. Now moving on to, or not, that's implications. Now moving on to equivalences. If and only if statements. Statement A is equivalent to statement B, logically equivalent, I should have said. Statement A is logically equivalent to statement B, provided that A implies B and B implies A. That's what it means, if and only if. A, if and only if B, A is logically equivalent to B, is the same thing as A implies B and B implies A. And so let's see what that turns out looking like in the truth table real quick. So if we have, let's do this column real quick. True implies true is?
True.
True implies false?
False.
False implies true?
True.
False implies false?
True.
True implies true?
True.
False implies true?
True.
True implies false?
False.
And false implies false?
True.
And now we're anding these two together. True and true is?
True.
False and true is?
True.
False and true.
False. False.
True and false?
False.
True and true?
True.
And so we notice A is equivalent to B, only when A and B have the same value. So if A and B are both true, or A and B are both false, then A is equivalent to B is true. That's what we mean. Logically equivalent, they have the same truth value. Logically equivalent. That make sense?
No, not quite. What was the outcome of that?
So, notice A is equivalent to B only when A and B have the same value.
So when it's true, then it's...
When they're both the same thing. When they're both true, it's true. When they're both false, it's true. But when one's true and one's false, it's false.
Okay.
So logically equivalent just means they have the same truth value. Anytime this statement's true, this statement's true. And anytime this statement's false, this statement's false. If that's the case, you're dealing with logically equivalent statements. Okay, so that's our quick run through of logic. We good there? Ready to continue? Now sets. Sets, my intuitive way of thinking about a set is it's an unordered, unique collection. Now remember, order doesn't matter inside a set, and duplicates don't matter inside a set. So here's 3 different ways of writing the exact same set. 1, 2, square, 2, square, square, 1, square, 2, 1. Changing the order doesn't matter. It's still the same set, and duplicates don't matter, it's still the same set. So all these sets are equal. Now how many objects are in the set? 3. It doesn't matter that I happen to have 4 pictures inside that set, there's still only 3 objects inside there. Because it's the same as these other sets, which obviously only have 3. Okay, so let's go over a bunch of notation. X is in A, or X is a member of A, or X is an element of A. I might say it all those different ways. So here's a symbol, X is in A, here's how we read it. X is a member or element of set A. X is in A, doesn't matter how we read it. So let's look at examples. True or false? 2 is in the set 1, 2.
True.
2's in here?
Yeah.
Yeah, okay. The set 1, 2 is in the set 1, 2, A, 13.
Yeah.
Yeah? Okay, the empty set is in the set containing this empty set.
Not true. I'm kidding.
True, right?
Yes.
And remember that this is shorthand for empty brackets. So all 3 of those were true? Oops. Alright, we'll get this one. Okay. So X is not a member of A, or X is not in A, however you want to read that, but that's what that symbol means. X is not a member of A, where A is a set. So this is a member of, put a line through it, means is not a member of. Alright. True or false? 2 is not a member of this set.
True.
True? All of you? Okay, now this one. The set containing 2 is not a member of that set.
True.
True? Alright. So they were all true.
Got
Have
it,
you seen
that
the
man.
false ones?
You were expecting a false one.
No, it wasn't.
You were expecting all true?
No. I don't have expectations.
No expectations. Smart. Okay, so let's go over some common sets real quick. So this set right here is the empty set. This set right here is
Natural numbers.
the set of natural numbers. Now, in discrete math, our natural numbers were 0, 1, 2, 3, 4, 5. In this class, the natural numbers start at 1. They're 1, 2, 3, 4, 5. And I told you that they go back and forth depending on the author. This author starts them at 1. The Z is
Integers.
the integers. Positive and negative whole numbers, including 0. The Q with the line through the right-hand side is
The rationals.
the rationals.
Okay.
So, you know what rational numbers are? Any numbers that can be expressed as fractions of integers.
Okay.
So the common example is the square root of 2 is not rational or is irrational. You probably came across.
Okay.
And then finally we have the reals, the real numbers.
What's the symbol for the complex numbers?
I think it's just that.
We could have guessed that.
random guess Q for rational.
I know. It's very weird.
Yeah, but we already have R for reals. Print? Wonderful, thank you.
You're welcome.
Okay. So, calculus, syllabus. I don't know why, man.
Wow, it's so bright.
Should we read these in the stupidest way possible? Yeah, I told him it doesn't need to be in color. It's just a program I use to do it.
This just seems like more blue than last year's, but last year is not blue.
Same program, so it's just whatever the printer uses. So going over that real quick, the grading works out exactly how I told you. The book I emailed to you. Make sure you have the book. If you don't have the book, let me know. And by the way, best way to get a hold of me is just text me. Don't email me. I'll never check my email. So if you need something from me, just text me and then I'll get to it whenever I can. I have my phone hooked up to my laptop, so I usually get it pretty instantly. Let's see. Oh, I didn't end up doing that. That must be for discrete math. Discrete math, I have to make the midterms and final take home to cut down the schedule.
You're gonna let them take the final home?
I had to cut out a bunch of days. That was the easiest way to do it.
How many weeks do we have?
26.
I thought we had 24.
No, you have 24
So we don't
on
have
one
any
day, 25 on 2 days, and 26 on Tuesday. So you have more Tuesdays than any other day.
Oh.
So we got lucky. You got lucky.
We don't have any room in the year, like last year, basically. Like last
For discrete math, there is no wiggle room. So I usually leave myself 3 weeks of wiggle
Are you
room,
trying to get them?
and I had to cut out 6 weeks.
You want to get them through groups or algebra, or are you just stopping with everything?
We're gonna go, we'll see how fast it goes. That class is, so this is a crazy year. This year, in both my classes, I'm teaching students I've already taught.
Right.
I've never just had one class where it was all students I've already taught. This year, I have 2 classes where it's all students I've already taught. So,
What do you mean
oh, so in discrete math, there's Emma, and then
Leah, Laura.
3 of my younger siblings who did my geometry, and then 1 more who's my nephew who
and logic.
did logic. So, all relatives.
Yeah.
So I thought this was going to be my biggest discrete math class ever because I knew for sure I was going to have 5 students in there. Turns out I was only going to have 5 students in there, which is very unusual.
Yeah, that is unusual.
No other people took it. There must have been some horror stories going around.
I
So.
recommended it to everyone.
I
just saying.
recommended it too.
Said it's one of the best math classes, and you'll have a great time. And it's hard, but it's worth it.
Well, maybe it's more a reflection on YouTube than it is on me.
So.
I don't trust your opinion. Anyways, yeah, so that's interesting. So I don't think that there's anything weird with this class. I think all the tests will be in class, all the finals and midterms will be in class, so we don't have to worry about anything like that. For this class, feel free to work with each other on homework. Feel free to look up online for solutions for homework. That's all perfectly fine. Just get the homework done. It's one of those things where even just understanding the homework problem, even if you didn't come up with a solution, is fantastic.
Better than nothing.
Far better than nothing. That's still a very good thing to help you understand the material. So do the homework. Something else I need to warn you guys about. So for the preliminaries, this doesn't matter, but once we get into the material, you need to read the book. This is not easy material that we're going to be covering. It's not going to be intuitive material. There's no way that I'm going to be able to just in class get it through to you. So you need to read the book. Don't be discouraged if you're reading the book and you don't understand what the author's talking about. You're making progress even if you think you're not. And you're getting comfortable with ideas even if you think you're not. If you read it ahead of class, then come to class and hear me talk about it, that's going to do you so much more good than just relying on me being able to on the fly give you everything that you need. That's not going to happen. That's not realistic. There's so many times in my college classes where students thought like I was taking the class again or something like that because I just came to the class prepared. That was the case in one of my classes called computation theory. There were a bunch of students that were convinced that I had failed the class and was retaking the class, and that is the only way that I was understanding the material as well as I did. And the idea that, no, I just made sure that I didn't just read the textbook for this class, but remember that prereq class? I also read the textbook and understood everything in there. I didn't just go through it like you did and solve the problems. So it helps you a lot. It really, really does. That's not because I was some special smart kid. I knew some special smart kids. I wasn't one of them. It's just because I read the book. It does so much. So read the book. It's expected that you'll read the material and not completely understand everything. That's great. Then you come to class and I can hammer on those specific ideas. And once again, there's only 3 of you. We better understand everything I put on this board. There is no excuse for not understanding everything. There's only 3 of you, and none of you are like that weird straggler kid who kind of had to be in the class because they didn't really have a choice. You know? You got it. Easy peasy.
Wait, so next week we should come having read section 1.1?
Yeah, so read about the completeness axiom, read that before. You don't need to go back and read the preliminaries. The author, he just kind of throws it out there, hey, make sure you're comfortable with all this stuff. He goes over it really, really fast and hard. He doesn't give you really insight, he more just warns you, hey, you better know this, and here's how I'm going to use natural numbers type stuff. Okay, so continuing, let's see, we were talking about these sets, right? So, are we all comfortable with what each of these sets are? Because we're going to use these symbols all the time, so if one of them's not making sense, let's hammer it down now.
So the Q is just the fractions?
Yeah, it's fractions.
fractions.
It's fractions where the numerator and denominator have to be integers. They can't be decimal numbers.
Right. But like 2 over 1?
2 over 1,
So
exactly.
all the natural numbers as well?
Yeah, oh, thank you. Notice that everything in this set is a member of this set. Everything in the empty set is also a natural number. Every natural number is also an integer. Every integer is also a rational number. And every rational number is also a real. So yeah, that's a good point that you make and forgot. So they're all subsets of each other. That's a subset of that is a subset. I guess we haven't said subset yet, so never mind. But everything in there is also in there, everything in there is also in there, everything in there is also in there, everything in there is also in there. Okay. So when you come across something like x in n, that just means x is a natural number. When you come across x in z, that just means x is an integer. There's oftentimes that you're going to want to talk about an integer. This is how I'm going to represent it rather than writing out let x be an integer. I'm just going to write let x in z, something like that. So you'll see those referenced all the time. Set builder notation. I don't know when you come across set builder notation in typical math classes. I don't know if they do it in college algebra. I assume they do.
I don't ever remember going over it, but we used it.
We use it in discrete math a lot, but
We went over it in discrete math
yeah.
pretty early on.
But let's make sure we understand it. So set builder notation, how do we do it? We do some dummy variable, a colon, which you typically read as such that, and then some condition using that dummy variable. So a common example, let's say I want to write the set of all even numbers. How do I write that? I would do that's the set of all x. X is just my dummy variable, such that x is an integer and 2 divides x. 2 divides, are we all good with the divide symbol? Okay, so that makes sense. This right here is talking about the set of all evens. Anything weird in that notation? Let's do another one real quick. The natural numbers. What's natural numbers? That's the set of all z, where z is an integer and z is greater than or equal to 1. Now notice here I used an and symbol, here I use a comma. Typically when you just comma separate, you interpret it as and. So I might accidentally do this sometimes, and I might do it this way sometimes. I don't want to confuse you.
You might as well just do the column.
I most likely will do the comma just because it's shorter, but I don't know what I'll do. I'll be writing this. Just keep going, who knows. Okay, so let's do it real quick. Let's write this set using set builder notation. 1, 4, 9, 16, what's the pattern?
Perfect squares.
Yeah, we're writing out perfect squares. So how would I write that with set builder notation?
All x
So
such
set of
that
all x such that
x squared, no, x is in z.
x is in z, okay?
And x is squared, I don't know.
And x is squared.
X squared is in z.
X under say it.
The square root of x
Yes, that's what I should say.
Is in Z,
is in z.
is that right?
Doesn't it have to be the natural numbers and not the integers?
Doesn't, well, this statement actually works, but it's relying upon a theorem that probably isn't obvious.
Yeah.
So it just so happens that the square root of any integer, if it doesn't come out as a whole number, then it's irrational.
Read.
Yeah, so all the ones, so this happens to be all the integers that you can't take the square root of and have it come out as an integer. So if the square root is an integer, then you happen to be taking the square root of one of these numbers. So that happens to work, but that's a really weird way to write it, because you're relying on kind of a weird fact.
Mm-hmm.
So another way that we might write this is it's a set of all y such that y is equal to x squared and x
There we
is
go.
a natural number or an integer.
That makes more sense.
Actually, we can't do integer. Should have specified that before. The reason we couldn't is because then we'd have to have 0 here. Right? But the natural numbers start at 1. So this one works, the one we had before wasn't technically true. So it's a set of all y where y can be expressed as x squared and x is a natural number. Remember in this class, the natural numbers start at 1.
Okay, so if you didn't have that first set, could you get that by
If
going
I-
through this?
If I didn't have this set,
Yeah.
could I look at this and reconstruct this? Yeah.
Could you?
Yeah, so I'd say, I want to write the set of all y's, where y is equal to x squared, and x is a natural number.
So you would just start at the first natural number then?
You got a point there in the sense that here we had a particular order, but remember in a set, order doesn't
Right.
matter. So you can start with whichever one you want and end up with the same set, as long as you do it for every natural
Oh, you
number.
just go for every single.
Yeah, this is an infinite set. This is every natural number, or every perfect square of natural numbers. And that's ultimately what you give this to. So yeah, you should be able to go from this to this. Going from this to this is more fuzzy because, yeah, maybe that's most likely the pattern, but who knows, there could have been some other crazy pattern that just happened to look that way. So you should always be able to go from this to this, but from this to this, not necessarily. Okay, quantifiers. So the quantifiers are that upside down A symbol. We interpret that symbol as for all, or for each, or for every. And the other quantifier is that backwards E, which is there exists. So if I say for all x in n, that is for all natural numbers, or for all x, where x is a natural number, however you want to read this. The way I would read this is for all x in n, is what I would say, but that's the same thing as for all natural numbers. This is there exists x and z, or there exists an integer. We go with the two quantifiers and how to interpret them?
Yeah.
Okay. And then set equality. How do I know when two sets are equal? How do I know that this set is equal to this set?
They have the same elements.
Yeah, everything in this set is in this set, and everything in this set is in this set. Therefore, they're equal. That's ultimately what we're saying here. Set A is equal to B if and only if for all x in A, x is in B, and for all y in B, y is in A.
It's kind of like proving that they're subsets of each other, right?
Yeah, that would be a
Always
really simple theorem you prove from this. So this definition for equality, that would be something that you can prove. Another way of saying it, two sets are equal if and only if they have the same members. I think you get the idea there. Any question about set equality when sets are equal? And notice that this right here also gives you an outline of how you would prove that two sets are equal. If I say prove that set A is equal to B, you need to show that for every x in A, x is in B, and then you need to show that for everything in B, it's also in A. That's typically how we show two sets are equal.
Pretty simple.
Yeah.
They try it.
No, well,
Well, sometimes.
it's simple once you're comfortable with it. It's like all math. At first it's hard, and it's easy. Okay, definition of this symbol. This we call the subset symbol. We read this as A is a subset of B. What does it mean for A to be a subset of B? It means for all x in A, x is in B.
Right.
Everything in A is also in B. So is the set 1, 2 a subset of the set 1, 2, 3?
Yes.
Yeah? Is the set square triangle square a subset of the set square triangle?
No.
Yes.
It is.
No.
Everything in here is in here. Is square in here? Yep. Is triangle in here? Yep. Is square in here? Yep. Because these are actually the same set.
Yeah, they're equal, but yeah.
They're equal, so that's the point, is that equal sets are subsets of each other. A set is a subset of itself.
That makes
Yeah.
sense.
Everything in a set is also in the set.
Crazy.
It sounds stupid when you say it out loud, but it's one of those connections you gotta make. Every set's a subset of itself. Okay, now this symbol without the line underneath. So we often think about subset as kind of the same way we think about less than or equal. And then proper subset symbol we kind of think about as less than, but can't be equal. So A is a proper subset of B, means A is a subset of B and they're not equal. So down here, 1, 2 was a proper subset of 1, 2, 3, but square triangle square is not a proper subset of square triangle.
Oh,
Because they're
it's like,
Equal.
it can be a subset and it can be equal because that's the line.
Yeah, this one's the same as it's either a proper subset or they're equal.
Yeah.
This one's saying it's a subset, but they're not equal.
Okay.
So it's a proper subset.
Cool.
Make sense what a proper subset is? Okay. Now we get on to our, so those were relations, now we're getting on to operations.
Those were
Relations.
stop there.
Uh-huh. A is a subset of B.
The relation on
It's a relationship between the two things.
It's a relationship between the two. Yeah. A is a proper subset of B, that's a relationship between the two. Well, that's the difference between a relationship and an operation.
One operation gives you a new set. And
Right. A relationship is making a statement. We can call a relationship true or false. It's making a statement. We can apply logic to statements. An operation just gives you another set. If I take A union B, that just gives me another set. That's not something that we call true or false. I can call A a subset of B true or false. That's making a statement. It's saying that this is related to this in this way. A union B, that's not a statement. That's just an operation. It's just taking two sets, unioning them together, and giving me a set back out.
Yeah.
So let's define union. And notice that we're going to define these operations in terms of logic. So you build up logic, so like you can build up set theory, and when you define your set operations, you reference your logic. So when I say A union B, what do I mean? I mean the set of all x where x is in A or x is in B. Notice x is in A, that's a statement. X is in B, that's a statement. So we're saying statement or statement.
Right.
I might be hammering this home harder than I need to, I don't know. But I just want to make sure that we understand or can only be applied to two statements. I couldn't apply or to A union B or B union C. That doesn't make sense. Those aren't statements.
Yeah.
X is in A, that's a statement. X is in B, that's a statement. It's either true or false. Good? So we define A union B to be the set of all x where x is in A or x is in B. So if I have the set 1, 2 and the set 2, 3, then the union of those two sets is the set 1, 2, 3. Everything that's in one set or the other is in the resulting set. Similarly, we have intersection. A intersect B is how you read that. That's the set of all y where y is in A and y is in B. So the intersection of the set 1, 2 and the set 2, 3 is just a set containing 2. Good? Nothing weird there? Okay. And then this, the way that what the author calls a symbol, so sometimes we just call this set subtraction. The other way that we say this is the complement of A in B. I'll probably just say minus. But the author's going to say the complement of A in B is this set. I'm just going to say A minus B is this set. They mean the exact same thing. And you'll get more comfortable with using terminology complement in discrete math. We use it a lot, but it just means minus. So the complement of A and B, or A minus B, is a set of all Z where Z is in A and Z is not in B. One way you can think about it is to start out with everything in A, then get rid of everything that's in B. The resulting set, that's what you get. Oh, I don't know why I didn't write an example of that. So if we have the set 1, 2, and we do minus 2, 3, 4, the result is in the set what?
1.
Just 1. 1's the only thing in here that's not in here. Okay, so that's set operations. Those are the only operations we care about for this class. Moving on to lists. Now, remember, sets, we didn't care about repeats, we didn't care about order. Lists, we do care about repeats and we do care about order. So when we're doing lists, we use parentheses rather than curly braces. And now we're saying that order matters and duplicates matter. So the list 1, 2, 3 is not the same thing as the list 1, 2, 2, 3 is not the same thing as the list 3, 2, 1. These are all distinct lists. And to help your intuition, lists are what we use to represent a point. So the point 1, 2, 3 is not the same point as the point 1, 2, 2, 3 is not the same point as the point 3, 2, 1. Right? These are two different points in 3-dimensional space. That's a point in 4-dimensional space. Drastically different, right? Any questions about lists? Ordered collections where duplicates matter. So how many items are, let's go back to this. How many objects are in this set?
3.
There's only 3 objects in this set, right? How many objects are in this list?
4.
4. So duplicates now matter. Good? Okay. There's a special type of list that we like to talk about a lot. It's called
An ordered pair.
an ordered pair. There we go. An ordered pair. What's an ordered pair? It's just a 2-element list. A list with only 2 elements in it. We often call the things in here elements or members, same way that we reference them in sets. So 1, 2, 2, 1, x, y. Those are all just ordered pairs. Good with ordered pair? Moving on then to a relation.
I have a quick question. So you showed me how you can encode a list as a set, right? If you had an ordered pair that was 1, 2, it'd be the set containing 1, the set containing 1, 2.
Correct.
How do you do that with more than the 2 element?
So the way that we interpret a 3-element list, this is shorthand. The proper way to do it would be 1, 2, 3, and so it's really an ordered pair within an ordered pair, where you encode it the same way you encode sets.
And then you can...
You do the set encoding the exact same way that you did before.
I see.
So that's how you do longer lists. But we often don't bother keeping track of that encoding, and we just write it out like that. Shorthand. Okay. So we're good with lists and we're good with ordered pairs? No questions there? Alright, so we're ready for a relation. What's a relation? A relation is just a special type of set. It's a set where every element or every member inside there is an ordered pair. So this right here is a valid relation. It has the ordered pair 1, 2, square triangle, 4 squiggly. All perfectly valid objects, that's an ordered pair, or that's a relation. Everything in there is an ordered pair. Make sense? Kind of. We don't care about what's inside the ordered pair is the point. Right? All we care about is it's a set of ordered pairs.
Okay.
What
And
it happened to
it's
be.
a relation.
Pairs of, doesn't matter. If it's a relation.
Therefore it is.
Or therefore it is a relation, yeah. Every set of ordered pairs is just, we have a special name for it, it's a relation. Question. Is this a relation?
No.
No, right? Because everything in there is not an ordered pair.
Right.
It's not? If it's in there, then it's an ordered pair.
Oh, well. Okay, sure. Yeah, I guess.
It's a vacuously true statement. Let's try it out.
You got me there.
If X is in the empty set, then X is an ordered pair.
So the empty set is a relation.
That isn't always a true statement.
Why?
If false, is X in the empty set? No, nothing's in the empty set. So if false, then doesn't matter if that's true or false. In either case, the implication is true.
Right.
So yeah, the empty set, if we're talking about relations, we can call it the empty relation. Perfectly valid relation. Okay,
That means that, oh, yeah, that's obvious.
so a relation is a set where everything in there is an ordered pair. Good? Okay, moving on now to a function. What's a function? A function is a very special type of relation. So, a relation f is called a function, provided that whenever you have the ordered pair AB in there and AC in there, B equals C. In other words, if you have the same left-hand element twice, then they better go to the same right-hand element. Another way of saying it is every left-hand element goes to one and only one right-hand element. Pictorially, you're often used to seeing something like, we'll draw two scenarios. You see something like this, you say, oh yeah, that's a perfectly fine function. But when you see something like this, you say, no, that's not a function. And why is this a function and this not a function?
Because in the second one it matches.
Because in the second one, an x goes to two values. That's bad. We can't have x goes to 2 and x goes to negative 2. You can't plug in one x and get two y's out. But here, each x only goes to one y. So that's pictorially how you're used to seeing it. If you've done like college algebra trig, but from discrete math, we're used to thinking about it this way. Every left-hand element goes to one and only one right-hand element.
But if they have different x's, then they can have the same y.
Yeah, different x's can go to the same y, that's perfectly valid. But, well, yeah, we'll just say it like that. So let's look at these two relations and say whether it's a function or not. So F is the set 1, 2, 2, 3, 3, 3, 4, 7. Function, yes or no?
Yes.
Yes.
Yes. Every left-hand element goes to one and only one right-hand element. I could have added something like this in here. Is it still a function?
Yes.
Yes.
Yeah, because I didn't change it. That element was already in there. So this function is still a relation that only has 4 elements in there. Right?
Yeah, yeah.
Yeah. What about G? Is that a function?
No.
No, because we have 1 goes to 2 and 1 goes to 3, but 2 is not equal to 3. So here's our, looking at our definition, here's our AB, here's our AC, but B is not equal to C. Good? So that's all a function is, special type of relation, special type of ordered pairs. Now we have special notation that we like to use for functions. So if I have the ordered pair AB in F, then I like to say f of A equals B. So f of the left-hand element gives me the right-hand element.
Right.
Right. So using this f and this g, I'll stand over here. Using this f and this g, what's f of 1?
2.
2. What's f of 2?
3.
3. What's f of 3?
3.
3. What's f of 4?
7.
7. What's g of 4?
G is a new function.
What's g of 4?
7.
7. What's g of 11?
The
Star. What's g of 1?
2, 3.
It doesn't work. So the fact that you can't use this notation is another way to say, oh, it's not a function. Oops, I tried applying this notation to something that's just a relation, not a function. So the fact that this isn't defined, we can't say what this is, means that this is not a function.
So like, that's technically a way to prove that it's not. Like, you could use that and prove that it's not a function.
I mean, sure, yeah.
I mean, I doubt we'll ever need to prove something's not a function, but
It's a weird way to do it, but
it seems like
you trying to do this would show you that, oh, oops, I'm treating something as a function that's not a function.
Just to show 1, 2, 1, 3. Like that's a counterexample right there.
Yeah,
Yeah.
simple counterexample. Okay, so now the way that you're used to seeing functions from your algebra classes is something like f of x equals x squared, right? This was shorthand for writing your function. Your function is still just a set of ordered pairs that follows this rule, that's all it is. This is just a shorthand way for writing an infinite set, because there's an infinite number of things that this is talking about, right? Writing out some of those, what's inside that function? 1/2, 1/4 is in there, right? Because 1/2 squared is 1/4. 11 and 121 is in there, because 11 squared is 121. Square root of 2 and 2 is in there.
Wait, what? Why wouldn't it be f of x equals y squared?
So, this is saying how the right-hand element is related to the left-hand element. Plug in x for the left-hand element. So when I plug 11 in there,
Okay, so
then
we
my
already-
right-hand
we already
element,
have the set, and then we make the notation. And that's the relation.
this is shorthand for this set.
Alright.
And what is it saying? It's saying f of whatever you plug in here is your left-hand thing. I'll tell you the right-hand thing for any left-hand thing you give me. So I say, okay, what's the left-hand thing for 1/2, or what's the right-hand for 1/2? And that's 1/4. So if I find 1/2 in here, its right-hand element is 1/4. So this is telling you how to get the right-hand element from a particular left-hand element. And you do that for all the real numbers, and now you've written out this set. So what's another one in there?
4 and 16.
4 and 16, right? What's another one in there? -5 and 25. And we could write infinitely many. There's infinite, we can't write them all. So this is shorthand for that set of numbers, that function, that set of ordered pairs, that relation. Good?
Yes.
Okay. Now, some definitions. The domain. The domain of a function is a set of all its left-hand elements. That's the high-level way of thinking about it. So when I'm talking about the domain of f down here, what is it?
1, 2, 3,
It's
4.
1, 2, 3, 4. So, as an example, the domain of this function f down here is just a set 1, 2, 3, 4. The domain of f in general is a set of all x where there is some y such that xy is in the function. That's kind of weird at first until you see what it's saying.
Yeah.
In other words, it's the set of all the x that have a y paired with it in the function. That might be a better way to say it. Okay, and the counterpart to the domain is the image. The image is a set of all the right-hand elements in a function. So what's the image of f down here?
2, 3, 7 star.
2, 3, 7.
Oh,
That one was G.
you pointed at G.
Oh, I meant F, sorry.
Oh.
F. So 2, 3, 7, 3. So just 2, 3, and 7, right? 2, 3, 7. So the image of f is a set of all y's that have an x paired with them in the function. Good? Now notice with f, the domain was bigger than the image. Perfectly valid.
Yes.
Right.
Nothing weird about that. Okay. New notation. Well, we did it with domain and image. Okay. New notation. F colon A arrow B. What does this mean? This means f is a function from the set A to the set B. So what does that mean? That means f is a function from, we say that f is a function from A to B, provided that the domain of f is A and the image of f is a subset of B. So a typical example is looking at the function f of x equals x squared. Notice that this is a function from the real numbers to the real numbers. Why? Because the domain of this function, what's the domain of this function? Every real number. I can plug any real number into this and get a number out, right? So the domain of this function is all real numbers. But what's the image of this function?
So, real numbers.
No. Can I ever get a negative number out of
sorry,
here?
it's just the positive integers.
No, it's just in.
It's the natural numbers and 0, right?
It's just a square.
What are you talking about? 1/2 is in there. I can get 1/2.
So all positive numbers?
Every positive number in 0. When we graph it, what does it look like? It looks
Right.
like this.
Right, of course.
Alright?
Right,
The y value is always greater than or equal to 0.
right.
So, f from R to R, so this is a function from R to R, by f of x is equal to x squared. The domain is all real numbers, and the image is a subset of the real numbers. So when I say that f is a function from the real numbers to the real numbers, I'm guaranteeing two things. I'm guaranteeing that the domain is every real number, and that the image is a subset of the real numbers.
So it's okay. So f is a function from A to B if all B is in A.
No.
If B is a subset of A, isn't that the same thing?
No. Let's do another example. So let's say that A is the set 1, 2, 3, 4, and B is the set 5, 6, 7. Notice that these two have nothing in common. If I have a function that maps 1 to 5, 2 to 5, 3 to 7, 4 to 7, there's a perfectly valid function. So if f does this mapping, then f would be a function from A to B. Notice
So why did you give that example then
this one?
with the R's?
Because this is one that people who did algebra and trig would have come across much times. So they're used to saying that. They would have said something like, this function is not on 2.
It seems like you would come across quite a few examples where f is a function from A to B, and it can be a function from A to C. Is that
And it can be,
like we could change the real numbers to be a different set, and it goes to the two? Or like
yes, so we could have rewritten this. We haven't gone to interval notation, but maybe you guys are already comfortable with it. 0, comma, infinity. All the numbers starting and including 0 to infinity. F is a function from this to this. That's also the case. Because every number that comes out of here is either 0 or bigger. So all the outputs are between 0 and infinity. And all the inputs is all the real numbers.
Okay.
So that's also the case. Good?
Doesn't that technically mean all the numbers between 0 and infinity?
Including 0.
All the numbers?
Uh-huh.
It's not all the numbers. All the numbers don't come out of that. That's what I'm saying. Doesn't 0, comma, infinity, doesn't that include all of them?
It doesn't include negatives.
Okay, but, huh?
So another way for writing this set. So if I have the notation 0, comma, infinity, another way of writing that is a set of all real numbers such that x is greater than or equal to 0. So all the numbers greater than or equal to 0. That's what this means.
Okay, but that's not true.
Well, it's not true.
I'm so confused.
we're saying, so let's look at all the outputs that come out of here.
Equals x squared, right?
Yeah, that's the function we're talking about. So let's write some real quick. So f of, give me any number you want. I'll start with -3. So I can plug negative numbers in, but what does that give me? 9. A positive number.
And it's not like you'll get every single number.
You will.
I will.
How?
Okay, pick a number that you want me to get.
2.
2. Well, what would I plug in to get that? Square root of 2.
Oh.
Any number you want, plug in the square root of that number, and you'll get it.
I see.
Now notice we couldn't
Okay,
get
that makes
negative
more
2.
sense. Yeah.
Yeah, okay. So that's cooking now?
Yeah.
Wonderful. So that's for this example. Now back to this one where we were dealing with discrete sets. So here, f is a function from A to B. It didn't use all of B, but its domain is all of A, and its image is 5, 7, is a subset of 5, 6, 7. Make sense? Now, if I change this to, and I made 2 point to 6 instead, it's still a function, right? But now we have a special name for a function like that. We call it.
Why? You still have 3 and 4 pointing to 7.
Yeah, but we
Yeah,
use
that's
all
fine.
of B.
But notice I used all of B.
Oh, right.
So when you use all of B, when you use all of that second set, then we call the function onTo. An onTo function is a function where B isn't just or where your image isn't just a subset of B, but your image is actually equal to B. So f is a function from A to B means that the domain of f is A, and the image of f is a subset of B. Then f from A to B is onTo, provided that the image of f is B, and not just a subset of it.
Is that the only thing that makes it onto?
Yeah, that's the definition of onTo. You have to have a function from one set to another set, and that second set that it's to has to be the image. And we
That
dealt
was
a
more
lot with those.
complicated last year.
That's how it is. That's why I wish that people could do something like take discrete math twice, because the first time through it's just new ideas, new ideas, new ideas.
Yeah.
And then once you come across them again, you're like, it was really just that simple. It was really that easy. And that's often how it goes. And it's hard until it's not. Okay. I don't know what to do with this camera. Just point it over at are we already that far into class? Holy cow. Okay, let's just take a break. We'll do our break. And then when you come back, we grab some markers. Sure. I'll start erasing the board and putting up new stuff. Jeez, it's going by fast.
cause I like that other classroom better.
You do?
Yeah. Just cause
Just
like,
because of the desk?
you're closer to the board and like, it's 2 whiteboards. I don't know why this board bugs me so much, but it does.
Yeah, I don't like it. It's a mess.
Yeah.
But the nice thing about chalk is markers die, chalk doesn't.
Yeah. Why is our first homework on page 562?
Because it's in the appendix. So your first homework is just preliminary stuff, which the author would have, it has it set up so that you could skip over and not really do.
Okay.
See, like, yeah, this does seem pretty fast paced. It probably took us a month to get to.
I know, I feel
Functions
like
and
we
discrete
just
math.
freaking covered everything.
We covered 2 months of material just barely, so.
Okay, so we'll continue. Oh, we're not ready to build axioms yet. Let's finish the last two properties a function might have. So we talked about onto. If a function's from A to B, it's onto if it uses all of B. Next, we talked about a function being one-to-one. So a function f is one-to-one, provided that every right-hand element comes from a unique left-hand element. Or every right-hand element is paired with a unique left-hand element. Or in other words, two left-hand elements don't go to the same right-hand element. Make sense? So here's one that's not. So f, I forgot my equals. F equal to 1, 2, 3, negative 7, 4, 2. This is a perfectly valid function, right? But it's not one-to-one because 1 goes to 2 and 4 goes to 2. So it's not one-to-one. If we replace that 2 with anything other than negative 7, so 5, then it is now a one-to-one function. So a function is one-to-one provided that anytime I have x paired with b and y paired with b, then x is equal to y. Now I think that this is one of the ones where it's useful to think about its contrapositive. The contrapositive is if x isn't equal to y, then f of x is not equal to f of y. If the left-hand elements aren't the same, then the right-hand elements aren't the same. This one says if the right-hand elements are the same, then the left-hand elements are the same. This says if the left-hand elements aren't the same, then the right-hand elements aren't the same. They're saying the same thing. This is two different ways about talking about a one-to-one function. It's a contrapositive. Remember that.
So if it's like 1, 1, 2, 2, 3, 3,
then you're good.
then it's one-to-one?
One-to-one.
Oh.
Okay, and then a bijection is just a function that's one-to-one and onto. So notice it only makes sense to talk about a function as a bijection if it's a function from A to B. It has to be from A to B in order for us to call it a bijection because we can only talk about these types of functions as being onto.
Yeah.
We can talk about anything as being, any function as being one-to-one or not one-to-one. But onto only applies when you talk about a function from a set to a set. Because onto is specifically talking about how f relates to that second set. So a bijection, if it's one-to-one and onto, it has to be a function from A to B. Make sense?
Mm-hmm.
Okay. So that's it for functions. And now we're ready to start actually building up analysis. So there's two different ways that we could do this. There's two different ways that we could do this. One way is to, one way that they often do it is that they start out with the natural numbers and the axioms on the natural numbers, and they work their way up and they use the natural numbers to construct the integers, use the integers to construct the rationals, use the rationals to construct the reals. That's the way that a lot of people would teach a class like this. The other approach is to just say the real numbers is a set satisfied by these axioms, and just start out with that and work your way from there. We're going to do the latter because it's quicker. Saves us having to spend a bunch of weeks building up the real numbers. So the real numbers is the set that satisfies three sets of axioms. The first set of axioms are called the field axioms. The second set of axioms are called the positivity axioms. And then the third set of axioms is just the completeness axiom. So we'll go over each of those set of axioms. Now we'll start with the field axioms. And remember what the axioms are. These are just now basic assumptions that we're making. From here on out, we operate on these assumptions. So this is where analysis begins. So what's our first axiom? So we're saying maybe a bit more quickly. So we're saying whatever the real numbers are, whatever that set is, and whatever plus is on that set, and whatever times is on that set, whatever these things mean, we don't know what these things mean. We don't have a definition for what these things are. Okay? I know that you have been using these things all your life. Now pretend that you don't know what the real numbers are, you don't know what plus is, and you don't know what multiply is. Okay? And we're saying that this is a set, and these are the operations that satisfy these axioms and some other axioms that we get. Okay? So whatever that plus thing is, and whatever those real numbers are, we know for any two things, sorry, I didn't say in the real numbers, for any two x and y in the real numbers, we know whatever that plus is, x plus y is equal to y plus x. The order that you apply this plus doesn't matter.
How do you say for all x and y in the real numbers? How does that define the real numbers? Because that's circular.
We don't know anything about the real numbers. We don't know anything about plus, we don't know anything about times. Now what this axiom is saying, now we do know that for any two things in the real numbers, we have no clue what those things are. But for any two things in the real numbers, it doesn't matter what order I apply the plus to them.
Right.
We get the same thing out.
But that's just for plus and times.
Right, that's
So,
all.
like, technically, can you say, I mean, technically you are saying that. For all rational numbers, or real numbers,
For any two real numbers you pick, for any two real numbers,
addition and multiplication is
commutative.
commutative.
That's exactly what this is saying.
Don't you need to define multiplication and addition for the axiom to be useful?
Nope. Remember that when you put it in an axiom, it is an undefined term. It is a primitive symbol. So we could have done some set theoretical definition for plus, and some set theoretical definition for times, and some set theoretical definition for 0 and 1, and we could have worked with a lower set of axioms and build up to the real numbers. That is a possible way to do it.
That's what you wanted to do in logic.
Right, that's why I was hoping we would have done in logic. But here, we're starting with higher level axioms. We're saying rather than building up, we're going to start with just some assumptions. So we don't know anything about the real numbers, we don't know plus, we don't know times. Here's the first thing I'm telling you about it. I'm telling you that for any two elements in this set, it doesn't matter what order you apply the plus to them, and it doesn't matter what order you apply the times to them, you get the same thing out of the set. And one more thing we're assuming that these are closed operations. In other words, when I add two real numbers, I'm assuming that's a real number. When I multiply two real numbers, I'm assuming that's a real number. That's another assumption that we're making about these. So this set and these two closed operations, these are my assumptions I'm making about them.
So when you do this, you're just you're kind of assuming that people know what plus and times are, right?
No, throw out the window plus and times. Pretend that you have no clue about it. From here on out, when you use a plus symbol and you're plussing two terms, you can plus in any order you want, you get the same thing. All you need to know is that it's an operation. All you need to know is that it takes two terms and spits out a term.
So when do you start to understand what those mean? To use them and simplify things?
Axioms are what give them their meanings. So you're going to find out that just forcing them to satisfy these rules makes them operate exactly how you expect them to operate.
We already know how they operate.
So
It's basically saying just
here's one
generalize it.
point that you need that's kind of hard for you to do when you first start a class like this. You already have all this knowledge because you worked with these things so much that when you go to start proving things, it's hard to know where to start, what you can and you can't use. You often think, well, duh, and you just want to apply some operation that you're used to applying. You need to it's hard, you need to just let go of everything you know, pretend that you don't know anything about these. Pretend that instead of R here I wrote, we have some set A, we have some operation star, and we have some other operation circle. And whatever this star and this circle operation are, we're not sure what they do, but here's what we know for sure. We know that x star x is always equal to, x star y is equal to y star x for any two things in A, and x circle y and y circle x is always equal for any two elements in A.
Right.
So you need to kind of think about it this way, even though we're going to use these symbols.
So how do you know how to start plugging in numbers and actually using those?
Well, you're going to notice that one of these axioms are going to give us two numbers, 0 and 1.
And then you can build.
And using these axioms and those numbers, I can, with the field axioms, I can get any, for example, rational number you want. So you say, okay, how do I know that 1 plus 1 is 2 using these? You might say that, right? Well, I would actually define 2 to equal 1 plus 1. That would be my definition using these axioms. I would define 3 then to be 2 plus 1. Then you might want to prove something simple like, well, let's keep going. Now 4 is equal to 3 plus 1, and 5 is equal to 4 plus 1. So these are now our definitions. Right? We're saying whatever 1 plus 1 is, whatever 1 star 1 is, we now have a shorthand for that. This symbol. This symbol now means that. This symbol now means that. This symbol now means that. Because I was guaranteed that 1 was in there. I knew that this was an element in there. That's what these axioms are telling me. That it guarantees me 1's in A. So now I'm going to say, whenever you take 1 and you star it with itself, we're going to call that this thing.
And just keep starring it with itself. Like
And we're going to star that thing with 1, and whatever it gives us, we're going to call it that squiggly thing right there. And I don't know, this one seems like it should be a little bit more boxier, so we'll give it a boxy looking symbol, right? You kind of need to let go of all this knowledge that you have and understand exactly what it is you're working with. And we can prove some basic things that you're used to proving. So now I want to prove something like 2 plus 3 is equal to 5. Let's prove that with our definitions that we have up here. Okay? So we can work with our left-hand side to get our right-hand side, or our right-hand side to get our left-hand side. We typically work with this to get this. So I know that 2 plus 3 is equal to is equal to 1 plus 1 plus 3, right? That's what 2 is. Now I'm going to apply associativity. That's the same thing as 1 plus 3. That's using my associative axiom, right? Now, plus is commutative, so I can change the order of the 1 plus 3. So I can do this as 1 plus 3 plus 1. 3 plus 1 by definition is that boxy looking thing. So that's the same thing as 1 plus 4 is the same thing as 4 plus 1 is the same thing as 5. So 2 plus 3 is 5. Proved it. And I can continue to prove all the things that you know and love. But they follow from these axioms. You don't need to have any previous knowledge of what plus is, of what times is, or what the real numbers are. And everything we do still works. And it all works as expected. So, we really are not making any assumptions other than exactly what we're saying here. Other than the fact that these are closed. The author gave a little paragraph before he gave the axioms that specified these are closed, and well, that's the only assumption he put there. So if these are closed operations on this set and they satisfy these, then we're going to be able to do all the math that we know and love with plus and multiplication as expected. Make sense? So let's go over the axioms, make sure they all make sense. So number 1 is just saying plus and multiplication are commutative. You're used to that. Number 2 is just saying that they're what? Associative. Number 3 is saying that we're guaranteed that there exists some element in there, we're calling it 0, such that for any element in there, when you do 0 plus it, you just get out that element. In other words, we're saying 0 is the additive identity. When you do 0 plus anything, you get that same thing. We know that's a property of this one number in there. So we now know that 0 is a number in there. And we now know that 0 star anything just gives you back that thing. Make sense? Similarly with 1. We now know that there's a 1 element in there, such that for any element, when you do 1, circle that thing, you just get that thing back out.
Okay.
Make sense? Okay? Number 5 is saying every element has an additive inverse, is one way you say it. So for every element in there, for every x, there exists some y, such that when you star them together, you get 0. You get the additive identity.
Oh. Right.
Similarly, we're saying for every x in there, where x isn't 0, then there is some y, such that their product gives you the multiplicative identity. And you see how this starts to give us fractions. So if I defined 3 to equal 2 plus 1, well now, since I have a definition of 3, this axiom now gives me 1/3. Because now this axiom guarantees me that there's something I can multiply 3 by, come up with any fancy symbol we want for it, I'll come up with that symbol, such that they're equal to 1. So since I knew that 3 was in there, I now know that 1/3 is in there. You see how that works and how these axioms start forcing all the numbers we know and love to be in this set?
Yeah.
Almost all the numbers we know and love. Forces all the rationals to be in there. And we'll get to the rest of them, the irrationals, later. But continuing. And then this one, this is what property?
Distributive.
Yeah, distributive property. This tells us what do we do when we have our stars and our circles showing up in the same equation and you're applying them to each other. Well, you can just distribute them like that, or you can undo it like that, however you want. And then finally, the non-trivial assumption, we kind of made this when I was listing those numbers out there, that 0 isn't equal to 1. Because it's possible, without this, that the only thing in there is 0. So if you get rid of this axiom, it's possible that everything in there is just 0. The same element. Not 0 the way that we know it, but it's possible that it's just a one-element set that satisfies all this. So this forces it to be a non-trivial set. Okay. Now, so those are the field axioms. So let's start doing some basic proofs using those axioms, and then we'll go from there. So, how much of that whiteboard can I see on the camera? I'm just going to move the camera so I can work on the whiteboard. We probably lost some stuff. Oops. I was sick of working on the chalkboard. But then you can't see the axioms we're referencing. Oh well. Tough luck for you guys. Okay, so let's do some proofs. So let's do proof there is only one 0 element. What do we mean by this? We mean that there's only one element in all the real numbers that has this property. That has a property such that when you add it to x, you get x right back out. Make sense? So, are we good with proof by way of contradiction? So, 1, assume by way of contradiction that there exists some 0 prime element in there, some 0 prime element in R, such that 0 prime plus x is equal to x, and x is not equal to, or sorry, not x, and 0 prime is not equal to 0. So assume, by way of contradiction, that there is some other element in the real numbers, such that when you add with that element, it acts the same way 0 does. But that number is also not 0. And we're going to show that's impossible. So there's only one element that acts like this. There's only one 0 element. It's kind of a weird way to say it, but I think you understand what I'm saying, right?
Yeah.
So, let's see. 2. Then we have, well, let's just see how I did here. No, I don't like doing it that way. How did I do it over there?
Oh, it's number,
Did you see it?
3rd from the bottom.
3rd from the bottom.
It's number 1.
You show that it actually, there's contradiction.
Oh, yeah, okay. So then we have 0 prime is equal to 0 plus 0 prime using our axioms. Now notice that's using this axiom. This axiom says any 0 plus anything is just that thing again. So 0 plus 0 prime is 0 prime. So 0 plus 0 prime is just 0 prime, right? Then use commutativity. That's the same thing as 0 prime plus 0, right? And now using our assumption, remember 0 prime plus anything just gives you back out that thing. 0 prime plus anything just gives you back out that thing. So I have 0 prime is equal to 0, contradiction. Because we assumed 0 prime was not equal to 0, we got 0 prime is equal to 0. 3, therefore there's only 1. Only 1 0 element, however you want to say that. And then that box, and we're done. Any questions with that proof? Kind of weird, right?
No.
No? Not really. Makes perfect sense.
Yeah.
Oh, awesome. All right, next, let's prove that any number times 0 is equal to 0. Prove that 0 times x is equal to 0. So 1, let x be some element in R. Doesn't matter what element. 2, then 0 is equal to 0 plus 0. Good with that? 0 plus anything just gives you that thing. And then, here's one that might feel weird for you. You guys in logic are going to understand why this works. X times 0 is equal to x times 0 plus 0. So you might be wondering, where in our axioms does it say I can multiply both sides by the same thing?
Is it equal 0 on both sides?
Well, it's not obvious why I can multiply both sides by x. None of these axioms say that I can do that. And the reason is because doing this is actually a rule of logic, not a rule of math. So math uses logic. And so it's a rule of logic, it's a rule of identity that for any operation circle, if x circle y is equal to x, sorry, I did it backwards. If x is equal to y, then x for any operation, circle is just any arbitrary operation, x circle z is equal to y circle z. The reason that's true is because I can substitute, I can rewrite this as y circle z is equal to y circle z.
Right, because x equals y.
Because x equals y.
And z
So this is true in logic,
Okay.
that the same thing is equal to itself.
Right.
So we can, if we have this, we can multiply both sides by the same thing and it's still equal. We can do that with any operation, not just multiply. Any operation, perfectly valid. So it's a rule of logic, it's not a rule of math, which is why it's not anywhere stated in our axioms. We're not relying on our axioms, we're relying on something more fundamental, just
How
logic.
do we know that 0 plus 0 equals 0?
Okay, so that one we do have from our axioms, and that is from this axiom. 0 plus anything is just that thing. So 0 plus 0 is 0. Make sense? Okay, so we have this, then using our rule of logic, we're allowed to multiply both sides by the same thing. And that would be the weirdest step, but then from here on out, I think you'll see it. Oh, shoot. I'm doing this how we did it in the other one. I don't have my cancellation on. Pause. Let's do another proof real quick. I guess I could just look at how I did in the book, but this isn't that. It's cool to just see these proofs anyways. So we're going to do our left-hand cancellation law. We're going to prove that if x plus y is equal to x plus z, then y is equal to z. So notice that this is the inverse. So over here we were going from, we can multiply both sides by the same thing, or add both sides, the same thing to both sides. Here we're saying we can get rid of that for both sides and just end up with y equals z. So that's what we're going to prove real quick. So that's not a rule of logic. This is something we need to prove, and then I'll use it in my proof over there.
You have to
So-
define negative first.
I don't have to define negative, but look at what this gives me. Axiom 5 says for any x, there exists a y such that their sum is 0. This is how we end up getting negative numbers in our system.
That basically-
It's from this axiom.
Basically defining negatives.
So, 1, let x such that x plus y is equal to x plus z. So I need to use that information to prove that y is equal to z, right? Now, observe that there exists some, I'll call it u, in R, such that x plus u, x plus the letter u is equal to 0. This is using axiom 5.
Right.
Axiom 5 says that for any x you have, I'm guaranteed that there is some y such that their sum is 0. That's what I'm using here. So x is a real number, so I'm guaranteed that there exists some u such that their sum equals 0. Right? So 3. Then, taking this, using our rule of logic that we can add u to both sides, x plus y plus u is equal to x plus z plus u, right? Perfectly valid. Lost you on that step? Just need to look at for a second.
X plus u equals 0. How can you just add u to both sides?
How can I add u to both sides? That's our rule of logic. Our rule of logic says for any operation, maybe keep this over here. For any operation,
Oh, right, okay.
x equal to y implies x circle
Right, you just explained that.
z. No, it's a good question because I remember when I was doing this, I'd often get stuck on that. Now I always wonder, how the heck are they justifying adding to both sides?
Because they're equal. Right, okay.
And I didn't have that question answered until we did this logic course over the summer. So, always learning new things. Okay, so you're good with we can add u to both sides. Okay, so then that gives us, if we rewrite it as, we can rewrite this as y plus x plus u is equal to z plus x plus u, right? And x plus u is 0. So we end up with, that gives us y is equal to z. So, we can do it. So if we have x plus something and x plus something, those two somethings are equal. Now I'm going to use that in my proof I'm doing over here. So keep going the way that we were doing it. This, on the left-hand side, I'm going to plus 0. On the right-hand side, I'm just going to distribute. So on the left-hand side, we have x times 0 plus 0. Didn't change it, just added 0. Is equal to, on the right-hand side, we distribute x times 0 plus x times 0.
You can use your left
Good.
translation.
3. Then, using what I just proved over here, I can cancel out the left-hand elements. So then, 0 is equal to x times 0. Is equal to 0 times x, using the fact that it's commutative. We're trying to show that 0 is equal to 0 times x, not x times 0. So. And we're done.
Cool.
Any questions on either of those?
When do we show that order really doesn't matter? In a lot of this. Like,
What do you mean that order doesn't matter?
in adding and multiplication. So, for example, we've just proved left-hand cancellation, right?
Yeah?
When can we just start to cancel things without taking the step to shift it over?
Oh, well that's just using this and using the fact that things are commutative.
At the same time?
Yeah. Well, and you're also using associative because we're actually being a little bit fast and loose when we write 3 terms like this. This is actually not technically valid. I have to put parentheses somewhere on that because I can only add 2 things at a time. But, so it's really using associative and commutative. I can always rewrite it so that the terms I want to cancel out are on the left-hand side and then cancel out. So I only need a left-hand cancellation. You might be thinking back to when we did group theory where we needed a left-hand and a right-hand cancellation. And that's because in groups, we didn't have commutativity. We only had associativity. So, we don't have to worry about that because commutativity makes our life a lot easier. Alright, let's do another one. Prove if A times B is equal to 0, then A is equal to 0 or B is equal to 0. That's a cool one that we didn't do last time. Oh shoot, I was going to leave that logic up there. Oh well, I think we've used enough time to review that. So, let's see. Prove if A times B is equal to 0, then A is equal to 0 or B is equal to 0. Understand what we're doing? Alright, 1. Let A and B be real numbers. 2. Observe that if A equals 0, then we're done.
Yep.
So in other words, from this point on in the proof, we're going to let A be not 0. So one of two cases, A 0 or A is not 0, right? If A is 0, then we're done. So 3 is going to be, then assume A is not 0.
By way of contradiction, or just assume A is not 0?
From here on out, we only have to deal with the case where A is not 0. If A is 0, our proof ends here. If A is not 0, we're going to finish and the proof ends somewhere else. It's the same thing as just handling two cases. It's just case 1 is a one-liner, so we didn't spend too much time specifying it.
Great.
Okay. 4. Since A isn't 0, what do we know about A?
It's, I don't know.
There exists the multiplicative inverse.
It has a multiplicative inverse, right? This one.
Right.
This is the only one that bothers to say anything about not being 0. So, then, there exists, we'll just use U again, U in R, such that A times U is equal to 1, right? Oh, oops. Let A be in R such that A times B is equal to 0. We're going to have to use that. Everyone okay with how I changed the starting line? Okay. So, we know A times B is equal to 0, 5. Then, A times B times U is equal to 0 times U, right? I can apply times U to both sides. That's that rule of logic. Nothing weird? Okay?
It can't be U though.
What?
Like, why is it U? Don't we
Well-
already have a U? Shouldn't it be different than U?
I start out with this equation.
Right, and then you can
And I said since A is not 0, there is a U with this property. So now I'm going to multiply both sides of my equation by U. I'm trying to get B equals 0.
how do those two U's even relate?
U is now a particular number.
Right.
U is the number that when you multiply it by A, you get 1. So it's some number. So now I'm just taking this equation and multiplying both sides by U, whatever that number is. We don't know what it is. Good?
Yeah.
So then, we can rewrite this as A times U times B is equal to, what's 0 times U? 0. We just proved that, right? So, that gives us that, which gives us, what's A times U?
1.
1, and 1 times B is
3.
B equal to 0. And we're done.
Yep.
So a times b equals 0, then either a is 0 or b is 0. One of those has to be true. Okay. Next, we're going to prove that there is a unique additive inverse. So remember, what this axiom says is, for every x, there's at least one y, such that when I add them, I get 0. What we're going to prove is that for every x, there's only one y, such that when you add them, you get 0. You see the slight difference in thinking? Okay.
Are we still, do you think we'll get through the positivity axioms today?
I have no clue. Jeez. Probably not. Definitely not.
Just we go through those in logic even.
Yeah, we did. I didn't. Those aren't all the ones we did in logic. No,
we had
no
like
less than
13,
simple.
didn't we? That's right. That's right.
Yeah. So shoot. We'll have to continue it next time, but let's get through as many as we can. Okay. So now we're proving that for all x in R, there exists one and only one. That's what the explanation point after the there exists means. There exists one and only one y in R. Y in R. Such, what is going on with me? Such that x plus y is equal to 0. Good? Okay. So, let x, y in R such that x plus y is equal to 0. 2, we're going to do proof by contradiction again. Assume, by way of contradiction, that there exists some y prime in R such that x plus y prime is equal to 0 and y is not equal to y prime. Good? 3. Then y prime is equal to y prime plus 0 is equal to y prime plus 0 is equal to y prime plus x plus y is equal to 0 plus y is equal to y. Contradiction. Any word steps in there? Right? So now we have a quick definition. So since there's one and only one y that satisfies this equation, we call that y negative x. What is negative x? It is the one and only one number such that when you add it to x, you get 0. So what is negative 3? It is the one and only number such that when you add it to 3, you get 0. What is negative 297? It is the one and only number such that when you add it to negative 297, you get 0. Make sense? So since we proved that there's one and only one number that satisfies that, we can now define that number. We're going to call that number negative x. So from there on out, that's what we mean by negative x. It's the thing that when you add it to whatever you're taking the negative of, you're guaranteed to get 0. So now we're going to do a proof that negative x is just equal to x. Make sense? Let x in R, let x be any real number, 2. Then the negative of x plus negative x is equal to what?
0.
0. Negative negative something plus that something is always 0. That's what negative means. 0, which is also equal to x plus negative x. Right? Now we can use that cancellation law that we used before to cancel out these two terms. And so we're left with negative x is equal to x. And we're done. Any questions? Feel like I did anything weird? Okay. We did that, we did that, we did that, we did that. Okay. Next one. Prove that negative 1 times x is equal to negative x. Let x in R. How did we do this in the other class? Do you remember how we did it? Because I felt like it was kind of elegant. Let's just play with it for a second because I don't really like how I have it here. Let's see, I know that 0 is equal to 1 plus negative 1, right? So then multiplying both sides by x, that gives me x times 0 is equal to x times 1. Well, let's write the x second. 1 times x plus negative 1 times x. Does that make sense? 0 is equal to 1 plus negative 1. That's the definition of negative 1. Multiply both sides by x gives me this. You good with that? So rewriting what I have right here, I have x plus negative 1 times x is equal to 0. So that gives me this. You good with that? 1 times x is just x. Negative 1 times x is negative 1 times x. X times 0 is 0. Yeah? Okay. Now remember, what is our definition of negative x? Oh, rather than using our definition, we'll just write it like this, which is equal to x plus negative x. Cancel out the x's on both sides, and you get negative 1 times x is equal to negative x. Anything weird?
One second. Just want to focus.
Sorry, this is definitely messier than how we did it in logic.
Yeah.
But all our steps are valid.
Good.
Okay. Were you good?
Yeah.
So, our next one is here's this. Proof that negative x times y is equal to negative x times y. Good? 1, let x, y in R such that, oh, not such that anything, just scratch the things in R. 2, then negative x times y is equal to, using our previous theorem, the previous thing we just proved, is equal to negative 1 times x times y. Remember, we showed that negative something is equal to negative 1 times that thing. That was the previous thing we just proved. Good? Our previous...
Why wouldn't you just distribute the negative?
We don't know that we can do that.
We haven't proved that.
How do we even know that we can do that? I mean, we have.
This to this,
No, up there.
this to this.
Yeah.
I'm proving we can do that. This is what I'm trying to prove.
Okay, but like, that doesn't look right.
Negative x times y is the same thing as negative x times y. Negative 3 times 5 is the same thing as negative 3 times 5. Or in other words, negative 15 is equal to negative 3 times 5, negative 15. Okay, so here's what we're proving. We did in the previous proof that negative something is the same thing as negative 1 times that thing, right? And this can be rewritten as parenthesis, parenthesis, negative 1 times x times y, right? And then once again, using the previous theorem, we know that negative 1 times something is the same thing as negative that thing.
Wait, what rule are you using to do that?
The same, I'm using the previous proof twice.
I'm saying to do what your previous said.
So our previous proof said that negative a is equal to negative 1 times a, right?
Okay.
So I know that negative a is equal to negative 1 times a, right? Now, just use distributivity, or commutativity and associativity, or just associativity in this case, right?
Yeah, just associativity. Okay, that's
Just
right.
associativity here. And then using this rule again, negative 1 times something is just negative that something. Negative 1 times something is just negative that something.
Oh, okay, that makes sense.
Why? And we're done. Alright? Next. Next we want to do proof that negative x times negative y is equal to x times y. So 1, let x and y be real numbers. 2, then let's see. Then x times y is equal to, so remember we proved that negative, that negative something is just that thing. We did negative a is just equal to a. Same thing here. And then notice that we could easily rewrite this as negative 1 times, just make all those negative 1s.
And what rule does that use?
That uses this rule.
Where did we prove that, right?
Yeah, we proved that. Sorry, it would have been better if I had what I had last time, where I had all our theorems listed out. That worked well. But we don't have time to do that. So, negative gives you back the same thing. Turn that negative into negative 1, turn that negative into negative 1. And now we can rewrite this as negative 1 times x times negative 1 times y. And then we can rewrite that as negative x times negative y. Right? So that takes care of that one. They say prove that 1 is equal to negative 1 times 1. So proof 1 is equal to negative 1 times negative 1. Well, we know that, observe that 1 is equal to 1 times 1. How do I know that? Yeah, our axiom says 1 times anything is just that thing. So it's also true for 1. So I know 1 times 1 is equal to 1, but I also know this is equal to negative 1 times negative 1 from what we just proved down here. Yeah. This one, sorry.
Yeah.
So 1 times 1 is negative 1 times negative 1, therefore 1 is equal to negative let's see, that's an exercise that you guys do. Oh, now we define subtraction. So definition. So remember we did our definition for negative x. I didn't write it out very well, but we had our definition for negative x. We now know what the definition of negative x is. What's the definition of negative x?
It's the number you add to x to make it 0.
It's the number you add to x to make the result 0. Okay, now we're going to define x minus y. What do we mean by x minus y? We mean x plus negative y. There's our definition for subtraction. So we now know how to subtract numbers. There we go.
Cool.
So you're going to do some proofs with distributing subtraction. Where do you give me my definition for multiplicative inverse? I'm missing something in my notes. Because we need to prove that there's one and only one multiplicative inverse, and then come up with a definition for that symbol.
I thought we already did that.
No, we did that for additive inverse. So we defined what negative x is. Negative x is a number such that when you add to x, such that when you add to x you get 0. Now I need to define multiplicative inverse. So x inverse, or to the negative 1, is going to be a number such that when you multiply by x, you get 1. That's what we're going to define that symbol to be, but first we need to prove that for any x, there exists one and only one number, as long as it's not 0, such that their product equals 1. And we didn't do that.
Well, let's just do it.
Yeah, let's just do it real quick. And maybe next time we can kind of like do a crash course re-go over of all this stuff to make sure we didn't miss anything.
Well, it will be, a lot of it will be in the appendix, right?
Well, I'll list over the proofs of these things. I mean, I'll try to have listed out all the theorems that we actually prove so that we can see it all and know what we can and can't do. Okay, what was I doing? Doing the same thing as this, except for slightly different. So, prove that for all x in R, where x is not equal to 0, comma, then there exists a unique y in R such that x times y is equal to 1. So remember, this axiom over here guarantees us that there is 6. This one guarantees us that there is some y that we can multiply x by to get 1, where x isn't 0. Now we're going to prove that there's only 1. Make sense of the leap that we're taking?
Yes.
Alright, so 1, let x in R, no, we need x and y. Let x, y in R such that x is not equal to 0 and x times y is equal to 1 to assume, by way of contradiction, that there exists some y prime in R such that x times y prime is equal to 1 and y prime is not equal to y. Basically, same exact way we did it right there. 3. Then y prime is equal to y prime times 1 is equal to y prime times x times y is equal to y prime times x times y is equal to 1 times y is equal to y. Contradiction.
Basically the exact same proof.
Yeah, they're identical. You notice that when we prove this for groups. And this is just two special cases of that exact same proof for groups, that there's only one identity element.
Why don't we just do that first? Do it once.
Because then we have to go over what a group is. In applying multiplication for groups, you have to be careful not to include 0 because 0 doesn't have an inverse. in terms of multiplication. It does for addition.
Well, didn't we do that here and set that x not equal to 0?
Yeah, but it's harder to build the framework of a group just to have a few shortcuts rather than just do double proofs.
Do we also need to say y not equal to 0, or?
No. We're saying if x is not equal to 0, then there's one and only one number in the real number such that the product gives me 1.
And just
And now we have our definition, by the way, for this symbol. So now, what is x inverse? That is a unique number such that when you multiply by x, you get 1. That's what x inverse is. The same way that negative x is a unique number that when you multiply by, or that when you add to x, you get 0. This is a unique number such that when you multiply, you get 1. And so we call x inverse, we call this a multiplicative inverse of x because it gives a multiplicative identity. Just like we call negative x the additive inverse of x because when you add them together, you get the additive identity. Right? Okay. We probably don't need to do this one. So the next one is prove that the inverse of the inverse gives you back the same number. That's going to be almost identical to a negative of a negative is the same number. I'll just write out that idea real quick, just in case you thought that there was something weird. I just won't write it out formally as a proof. So we know that x inverse is equal to 1 times x inverse is equal to x times x inverse times x inverse is equal to x times x inverse times x inverse. And remember that this is the inverse of that thing, and so this is 1. Almost identical to this one.
Well, okay then.
Combining the inverses. So we're going to show that negative A inverse is equal to negative A inverse. Maybe negative A inverse.
Okay.
So let's do that one real quick. Let's see, we know that negative A times negative A inverse is equal to 1.
Not equal to 1.
Yeah,
Oh, I thought that was a double.
that's the inverse of that thing.
Yeah.
I don't know why I wrote it like that. Write that over there. X and x inverse is equal to 1. I already know that. Nothing here. Oh, I was saying if that's true. Okay, sorry. I've changed my style in pretty many years, so I'm losing track of things. So negative times that, not that one. We already know that one's 0, but I actually meant it like how I had it the first time. Negative A inverse. Inverse like that. Okay, so let's just look at what that's equal to. So this is equal to, we have a negative and a negative.
Which is a positive.
So that just gives us A times A inverse, right? Which we know is equal to 1, which we know is also equal to negative A times negative A inverse. There we go. So we knew that this was equal to 1. The problem was showing that this is also equal to 1. Therefore, these two things are equal.
How is that not the same thing?
So this is saying, so let's pretend that A is 3 for a second.
Okay.
So this is saying negative 1/3. This is saying negative 3 to the power of negative 1.
Okay.
We're applying the negative first and then the inverse. Here we're applying the inverse first and then the negative. And basically what we're proving is the order that you apply those doesn't matter.
Okay.
Doing the inverse to the negative is the same thing as taking the negative of the inverse. The inverse of a negative is the negative of an inverse. So that's what we were proving. So we already know that this was equal to 1. The trick was showing that this is equal to 1. Then left-hand cancellation leaves these two are equal. Okay, so yep, we're done there. We'll call it good there and then continue next time. Get started on the homework, get going, and read the next section because we don't have that much more to cover in this section. Okay. We only have a couple more things we got through a decent amount.